Now let us actually examine what makes the nucleus of an atom a stable structure. So we're going to discuss the types of forces that exist within our nucleus of the atom, between our nucleons. And let's begin with the force that we have already spoken about. So let's discuss the force that exists between two like charges. So if we take two positive charges and we bring them close to one another, those two positive charges will feel a repulsive electric force as a result of one another. So we might expect that when we take protons which have a positive charge and we condense them into a very small region we call the nucleus, these protons will basically repel one another. So let's, for example, discuss the nucleus of the nitrogen atom. So in the nitrogen atom we have 7 protons and 7 neutrons. So when we condense these nucleons into this very concentrated region, we might expect that these protons, which each carry a certain quantity of charge, positive 1.6 times 10 to negative 19 coulombs, will basically exert a repulsive electric force that will destabilize the entire structure as a whole, because these protons will want to separate and move away from one another. So the question is, if the electrical forces act to actually destabilize the nucleus structure, what acts to stabilize it? That means there must be a force that acts between the nucleons of our atom that actually holds these nucleons together and creates an overall stable structure. And these forces are commonly known as nuclear forces. And because this type of force is stronger than electrical forces, we know, or we call this force the strong nuclear force. Now, the strong nuclear force is always attractive by nature, and it exists between any two nucleons. So the strong nuclear force exists between two protons, between two neutrons, and between a proton and our neutron. Now, electrical forces and gravitational forces are long range. That means these forces can act over very large distances. However, strong nuclear forces are forces we call short range forces because they only exist over very small distances, typically over distances that are on the order of 10 to the negative 15 meters or less. So this is the distance that only exists between the nucleons found in the nucleus of our atom. And if we get farther away, then these forces basically go to zero. So we see that these strong nuclear forces are the forces that stabilize the nucleons as a whole and that stabilize the nucleus and decrease the energy, while the electric forces are the forces that act to destabilize the nucleus of our atom. So basically, when we're building an atom, there is a constant competition between the repulsive electric forces that act to destabilize the nucleus and our strong nuclear forces that act to stabilize our structure. Now, let's go into more detail about the stability of nuclei of atom. So we know when we have one proton and one neutron in the nucleus of an atom, we only really have a strong nuclear force because the neutron has a net charge of 0, so that means there is no electric force between the proton and the neutron. However, what happens when we begin increasing the number of protons inside the nucleus of our atom? So let's read the following paragraph. So although electric repulsive forces destabilize the nucleus, strong nuclear forces act to stabilize it. Therefore, as we increase the number of protons in the nucleus of the atom, we increase the destabilizing electrical forces that act to basically increase the energy of the nucleus, and which act to basically separate our nucleons, our protons within the nucleus. Therefore, to compensate for this increase in instability due to the large number of protons or the increasing number of protons, we need to add more neutrons into our nucleus, because neutrons basically act to stabilize via our strong nuclear forces. So recall that neutrons, since they have a net charge of 0, feel only an attractive nuclear force due to one another, due to the other neutrons and protons, and therefore always act to basically stabilize our nucleus as a whole. So we can conclude the following conclusion. So stable nuclei tend to have the same exact number of protons as neutrons, because as we increase the number of protons, we must increase the number of neutrons to compensate for the higher repulsive electric forces between the greater number of protons. So stable nuclei tend to have the same number of protons as neutrons up to a certain atomic number, up to a certain number of protons, which we call 30. So when we have 30 protons in our nucleus, we'll have 30 neutrons in that nucleus, and that will still create a stable structure. Now, past this number, when we go higher than 30 protons in our nucleus, the high number of protons in the nucleus creates an overpowering repulsive electric force, and that force basically needs to be reduced by increasing the ratio of neutrons to protons. So 30 or below, the ratio of neutrons to protons is 1:1. When we go higher than 30 protons, the ratio of neutrons to protons becomes greater than 1. Now, the last atom that can exist as a stable entity, as a stable structure indefinitely without undergoing radioactive decay, is known as the lead atom, which basically contains an atomic number of 82. So it contains 82 protons inside the nucleus, but it contains many more neutrons, because the great electric forces that exist inside our nucleus as a result of the repulsion of the protons has to be compensated by increasing the ratio of the neutrons to protons. Now, we're going to get more into detail and discuss radioactive decay in the next several lectures. Now, another nuclear force that we haven't yet spoken about that exists, that is not the same as the strong nuclear force, but is weaker than the strong nuclear force, is known as our weak nuclear force. And we'll talk more about this force in a future lecture.